Yes, hi everyone. So, welcome back to Power Systems 2 online series. In the previous class, we studied about the reflected voltage, refracted voltage, and incident voltage. And similarly, we have written that is the same thing we can write for the current also like that. We have written the statement, and also we solve one problem. Okay. Yes, today what we see in the sense, suppose, and we know that the voltage and the currents are waves. Voltage and the currents are waves, and in the transmission line, how we take the traveling waves? How we take the traveling waves, and what is the velocity of the traveling wave? What is velocity of traveling wave? In your examination, they may ask the question: derive an expression for the velocity of the either voltage or current of the transmission line. Okay. Yes. Now let us we discuss about that today. Yes, and we know this keeps adding traveling waves on transmission line. Traveling waves on transmission line. Traveling waves on transmission line. Yes, we know that in the case of transmission lines, inductance, capacitance, and resistance are uniformly distributed over the length of transmission line. Yes, for steady state operation of the line, the transmission lines could be represented by lumped parameters. But for the transient behavior of the lines, they must be represented by their actual circuits, that is distributed parameter. Yes, we say that for a 50 Hz supply and a short transmission line, the sending end current is equal to the receiving end current, and the change in voltage from sending end to receiving end is very smooth, like that we assume. This is not so when transmission line is subjected to the transient. Yes, even though the transmission line is single phase, that is a short transmission line, and we know the length of short transmission line is less, but whatever the analysis we have done, that is valid only for the steady state operation. But whenever the transients occur, transients in the sense whenever the sudden change occur either in voltage or current, or we can also say the transient in the sense the fault conditions occur. Yes, then how we say, yes, how we consider, yes, in such case, so whatever the assumptions we made, whatever how we consider the distributed parameters as the lumped parameters, all will gives the wrong solution, wrong answers. So hence it is not correct when the transmission line is subjected to the transients. Okay, so generally how we take the transmission line, it is like this. Yes, let us we assume transients in the sense the sudden change in the system. Let's draw the circuit. We will see in detail about this in the fourth unit. This is sending in voltage, let it be V, and here I kept one switch. When switch is closed, then voltage and current from sending end to receiving end will be travel. Okay. Yes, this is actual when the transmission line is subjected to the transient. If suppose this is the line, as here we shown the line is just a simple line like that, but practically it is not simple line. Yes, how it is, resistance is there, inductance is there, capacitance is there, conductance is there, susceptance is there, like that. So how we represent the transmission line? Yes, we can represent in two ways. One is nominal T method and another one is nominal pi method. So in both ways we can represent. So let me take nominal pi method. Yes, nominal pi method in the sense at the sending end, receiving end, you may have the impedance. Yes, it is like this. Yes, so on. Yes. So here we may have the sending end, therefore it is sending in voltage Vs, and here let us we assume we connect one switch. Connect one switch, and the shunt parameters are like this. Sorry, here the capacitance is there. Let's draw the circuit. Yes, what you observe here, the transmission line contains the series resistance, series impedance, and shunt capacitance and shunt resistance. Shunt resistance is also taken as conductance. This is conductance G, and here it is susceptance B. Therefore, the admittance is G plus JV, and here it is series resistance is R. XL is line resistance, so that is R plus JX is the series impedance. So this is actual transmission line, that is exact actual transmission line is like this. Yes, for example, there is no loss in the transmission line. We assume that there is no loss in the transmission line. Then how it is? Yes, how it is? The resistance is 0 because the loss indicates only due to resistance in the transmission line, that is I square R like this. So if we remove the resistance, then the transmission line become lossless transmission. So let us we assume the transmission line is lossless. Transmission line is lossless. Then we can draw the circuit as this is switch. Here it is inductance, capacitance, inductance, capacitance, so on, inductance, load like this. Sending in voltage. So here we connect the switch L1, C1, L2, C2. This is LN, CN, and here it may be load. Okay. Yes, now it is desired to find out the expression for relation between the voltage and the current waves traveling over the transmission line and their velocity of propagation. Their velocity of propagation. Suppose that the wave after time, sometime, let us assume small t, small t has traveled through a distance x. The wave is during small t travels the distance x. Okay. Since we assume the lossless lines, whatever is the value of voltage and current waves at the starting, so they remain same throughout the travel, that is throughout the transmission. Yes, what is that? We assume that the transmission line is lossless. When the transmission line is lossless, when the transmission line is lossless, so hence what we say, the value of voltage and current waves, whatever the value of voltage and current waves at the starting, they remain same throughout the traveling. Let's consider the dx, that is small distance, so which is traveled by the waves in the time dt. Dx dt. Yes, dx dt. The electrostatic flux is associated with the voltage wave and electromagnetic flux with the current wave. The electrostatic flux, which is equal to the charge between the conductor of the line up to distance dx, is given by, as we know that q is equal to cv. CVX. Yes, then the current in the conductor. Yes, we know that what is equation for current? I is equal to dq by dt. Yes, now let us differentiate this. Differentiate this, we will get, substitute the value of q here. That is I is equal to d by dt of CVX. Or we can also write the equation as I is equal to Vc into dx by dt. Yes, Vc into dx by dt. Now dx by dt in the sense distance by time. Yes, distance by time. Yes, distance by time indicates, what is distance by time? Velocity of the traveling wave. Yes. So hence here dx by dt is the velocity of traveling wave over the line conductor, and let us we assume that is represented by small v. Let us we represent the velocity of the transmission line is small v. So hence we can write I as I is equal to CV small v or Vc small v. Similarly, the electromagnetic flux linkages created around the conductors due to the current flowing in them up to a distance of x meter. Yes, then the flux linkage at x is given by, yes, x psi is equal to I L x. Yes, this is I into L into, yes, x is, as we assume there is small change in charge. Yes, therefore this you can write as V, because V is equal to d psi by dt. So as we know that the electric voltage is rate of change of flux linkage. Electric voltage is rate of change of flux linkage. So hence we can write the expression for V as V is equal to d psi by dt. d psi by dt. So hence this value is IL into dx by dt. So we got this value. Yes. So here if you substitute dx by dt as V, then V is equal to IL V. IL V. Okay. Now let us divide this equation with the previous, that is V by I. Let us do that one. V by I. Yes, what is V? Yes, what is V? V is equal to IL V. Now what is I? Is V C V. So V get cancelled. This is I by C into L by C. Because V get cancelled, I by C into I by V into L by C. Okay. Or you can also write V square by I square. That is V by I, which is called natural impedance or surge impedance. This V by I is equal to square root of L by C, and this is equal to Zn, where Zn is natural. So here the expression is the ratio of voltage to current, which has the dimensions of impedance and is therefore here designated as surge impedance. Yes, I told you surge impedance or natural impedance of the line. It is also known as the natural impedance because this impedance has nothing to do with the load impedance. It is purely the characteristic of the transmission line. The value of this impedance is about 400 ohms for single phase transmission line and 940 ohms for cables. Yes, 40 ohms for cables. So now let us we multiply V and I. So we find V by I. Similarly V into I. V into I. Yes, V into I indicates V C V into I L V. Or you can also write this equation as V I L C V square. This is V I L C V square. Yes, from this here this is equation for V. So V get cancelled, I is also get cancelled. So hence V square is equal to 1 by L. This implies V is equal to 1 by 2 pi, or it is 2 pi is not 1 by root LC. This is velocity, and we know that what is equation for L and what is equation for C from the first unit. So where L is equal to 2 into 10 power minus 7 ln d by r or Henry per meter. And similarly, what is C? 2 by epsilon 2 by epsilon s divided by ln d by r. So now we substitute L and C in the velocity equation. This V is equal to 1 by 2 into yes 2 into 10 power minus 7 ln d by r, and similarly 2 by epsilon ln d by r. Yes, dy ln dy. So these two will get cancelled. Now what is the remaining thing? Velocity V is equal to 1 by 4 pi epsilon into 10 power minus 7. Yes, 10 power minus 7. So okay, now we substitute as now we substitute the value of epsilon naught. Epsilon naught is equal to 8.854 into 10 power minus 12 farad per meter. So hence you substitute that value, then you will get the value of V as V is equal to 3 into 10 power minus 8 3 into 10 power 8 meter per second. I think you can remember this value. So where you got this value? This is the velocity of line. This means the velocity of propagation of the traveling waves over the overhead transmission lines equal to the velocity of the light. This statement is very, very important, and even in the examinations also you may get the direct question. Yes, what is that? The velocity of propagation of the traveling waves over the overhead transmission lines equal to velocity of light. Show that or prove that. Yes, you need to prove by doing all these things. Okay, in actual practice, because of the resistance and leakage of the lines, the velocity of the traveling wave is slightly less than the velocity of the light. Normally a velocity of approximately 250 meters per microseconds is assumed. Yes, it can be 250 meters per microsecond. Yes, it can be seen from the above expression that the velocity of this line over the cables will similar than over the overhead transmission line, because of the permittivity term is not permitted term in the denominator. Okay, since epsilon is equal to epsilon naught into epsilon r, for overhead lines epsilon r is equal to 1 because it is in the free space or air, whereas for cables for conductors, where the conductor is surrounded by some dielectric material for which epsilon r is greater than 1. Okay, this is about today's topic. That is, we can conclude that the velocity of propagation voltage and current over the transmission line is equal to the velocity of the light, which is 3 into 10 power 8 meter per second. You should check that. Yes, thank you for listening this. Have a nice day. Thank you once again.